All right, so we were talking about two force bodies. Well, one thing we can do is to use this principle to very easily figure out where our center of mass is experimentally. So if I have this piece of paper, obviously it's a uniform thickness. It's just 8.5 by 11. We know that the center of mass would be right in the center. But you can see that if I were to pin this in any spot and it drops down, and so I have a force pulling up on it, and the weight, of course, is pulling down, and we know that those forces must be equal in magnitude, opposite in direction, and collinear. So I could just draw a line straight down, and that would have to pass through the center of mass of this object, of this piece of paper. And then if I held it someplace else, like here, right? If I held it right here, then same thing. If I drew a line straight down, it would have to pass through the center of mass. So the intersection of those two lines would be where the location of the center of mass of this piece of paper is. And of course, if it were a three-dimensional object, in other words, it had some reasonable width here, I could do this I could also hold it in some other spot, and then we would have three lines, and the intersection of those three lines would be where the center of mass is. So if we look at a robot, so here's a VEX robot, and we want to determine where the center of mass is. Actually, let me just back up for a second here. One thing in doing this technique, you want to hold it at a spot that's above the center of mass. I could actually do the same thing. It'd still be a two force, right? If I could just balance it just right, get my force up just underneath the weight, but it would be an unstable equilibrium, right? Any kind of vibration or anything, and it swings down like this. So if you're trying to um, determine, if I want to determine the X location of the center mass, you don't want to try and like balance it underneath. You might be a good balancer, but it's unstable. So a better idea would be to turn it upside down. So now the center of mass is lower, and if I put my fingers, so suppose I put my fingers two holes back from the wheel here, and you can see if I hold it, so it's not quite even. It's not quite level. If I go back to 3 holes back, then it's still not quite level. If I put my fingers right in between those 2 holes, perfect. So now I just put a little mark here, and now I can just measure that, say with respect to one of the axles, and I know the X location in the center mass. Now if I want to find the Y location, I'm going to do that by bouncing on these bars right here. So you can see if I balance like this, it's not level. If I come too far forward this way, it's not level. And if I move my fingers to just the right spot until it's perfectly, well, perpendicular to the ground, then I know the center mass has to be passing through a line through that point. And I just put a little mark here. You can see that little green mark. And now I can measure that from, put it on the ground or the rug or whatever, and measure up to that. So now I know the X and Y location of the center of mass of this robot. And of course, if I weigh it, now I could do the same thing to determine the center of mass this way. This robot's pretty symmetrical, so I'm expecting it's going to be, pretty much in the center in this direction. But anyways, this is a real quick and easy way to figure out where the center of mass of a system is.